Hi everyone, welcome to another tutorial on using Excel. In this video, we'll look at an intuitive introduction to estimation or regression using Excel tools. This will only be a primer, and a lot of the technical aspects of regression will be reserved for future videos. We'll start off by looking at a couple of different problems that we generally tend to encounter. The first problem is drawn from the manufacturing industry. In this, given in column B and C, we have the number of units and the total cost of production. For example, if you look at row number 5, it says to manufacture 175 units, the total cost was 875. Similarly, to manufacture 90 units, the cost was 630. The question that we're being asked, given this data set, is what can be the expected cost if, let's say, 150 units are produced by the manufacturing unit? So this is a kind of manufacturing problem that we frequently encounter. Similarly, if you look at problem 2, which is drawn from the service industry, we have data in columns H and I. First column talks about the number of agents logged in. Second column talks about the number of calls taken by those agents in a given day. So if you were to take an example of row number 5, it says 59 agents took 1469 calls in a given day, and then 58 agents took 1445 calls in a given day. The question that we're being asked is what can be the expected calls taken if 53 agents are logged in to take calls on a given day. So these are typical estimation problems. These can be addressed in a number of different ways, and there exists quite a lot of different quantitative and mathematical tools to do so. Today we'll take a understanding of how this can be done in a very simple way using Excel. And like I said, that this will only be a primer. A lot of the complicated quantitative mathematics is going to be reserved for later. So in order to do this, the first thing that we need to understand is how are such problems generally approached. So any data analysis problem, and if any of you have worked on data analysis problems before, while you can apply statistical methods, hard maths to any of these problems, remember that a lot of these problems begin with looking at a graphical interpretation of what the data really means. So let's take a deeper dive into this by understanding this data further. So what we have here is the same data set. We'll use the manufacturing problem as an example here. So we have the same data replicated in columns B and C. We have the number of units, the total cost, and the questions mentioned there as well. We want to estimate the cost if 150 units are produced. What we have on the right hand side is a scatter plot. Now a scatter plot is a tool, a graphical tool, which can be used very frequently with both continuous data forms and discrete data forms. That is, if your independent variable or your y, as well as, or in fact your independent variable or your x and your dependent variable and your y can be represented as continuous and or discrete, then you will be able to look at the data graphically by using a scatter plot. How to build a scatter plot, we'll look at that later. For now, we already have a scatter plot available to us. On the x-axis, we have the number of units. On the y-axis, we have the total cost, and the data has been plotted. This data that you see in columns B and C has been plotted on the graph here from columns E till column M. So the moment you look at this scatter plot, one thing which is immediately apparent to us is that a lot of these points appear to be very close to some sort of a hypothetical line. In other words, while this data is not linear, strictly speaking, but they lie very close to the approximation of a line. So for instance, if we were to, let's say, draw a line or attempt to draw a line which is as close as possible to all of these data points. So for instance, let's say we were to draw this line, we can just quickly change its color. There we are. So this orange colored line that you have here is a line which doesn't intersect all the data points but comes very close to all of them. And yes, it is possible for us to draw multiple different lines which come very close to these data points. But let's say for this example, let's say this is a line which comes very close to this data point. So in other words, if we have a pattern which is going to mimic the data that we have, so all of these data points that we have here, if they can be approximated by a straight line, then the advantage that we have to gain from this is when we want to estimate the cost for, let's say, 150 units. Given this line, what we might be able to do is get an approximation of what that cost is. All that we'll have to do is, from the 150 units, if you draw a vertical line which intersects this approximate straight line which gives us all the data points, then whatever this point is will be able to then give us what the possible or expected anticipated cost might be, right? And as we can see here, that anticipated cost then will come somewhere in between 1000 to 1100, and later on we'll see what that cost might turn out to be. But then basically that is the advantage. If we are able to approximate these points by a straight line, then and remember that all straight lines have a certain mathematical variant or a mathematical equation, so then we'll be able to probably substitute the value of x with 150 and get the value of y, which will then give us the total cost. So before we move on further, it might be helpful to just quickly take a look at some more information about straight lines. Now, we all know from high school mathematics that straight lines, one of the standard ways in which straight lines are represented is the form y equals mx plus c, where y is the dependent variable, m is the slope, x is the independent variable, and c is the intercept on the x-axis. So given that formulation, if we were to apply this formulation to our problem here, which is estimating the cost, remember that the cost is going to be your dependent variable, or y, and your x is going to be your independent variable, or your number of units being manufactured. So with that formulation in mind, that you could possibly represent a straight line as y equals mx plus c, remember that if by any way, if by using any method, if we are able to calculate the m and the c of this line, then by substituting the value of x as 150, we'll be able to get the cost of y. So this is the benefit, this is the great advantage of being able to approximate those points that we just saw with a straight line. Couple of different things about this. Now remember that just because one independent variable and a dependent variable y seem to move together or seem to change together is not an evidence of causality. So remember, when we look at this, we are only looking at possible correlation. We are not looking at causality. And causality is again something that we'll cover in another video. But for now, remember that just because two different variables like cost and number of units manufactured seem to be moving together in a linear fashion does not necessarily mean that we have evidence for causality. We are just looking at correlation. We are looking at the amount of change that we can explain in cost given the amount of change that we have in the number of manufacturing units. And again, we'll revisit causality versus correlation at a later time. Now, another important thing for us to understand is, let's say you were to plot the independent variable y along with the dependent variable y along with the independent variable x. On the left hand side, you have a certain graph. As you can see, that the line which approximates the data points, this is this green colored line that you see moving upwards. And whenever you have a correlation between two variables like this, this is usually an indication of a positive correlation, which means if x increases, y also increases. On the right hand side, what you have is an example of a negative correlation. So this is the type of correlation where when x increases, y will decrease. So this is an example of a negative correlation. Now, let's take this forward again. So here we have a couple of different graphs. They are again representing the same manufacturing problem that we looked at, which is cost versus the number of units being manufactured. So let's attempt to approximate it by a straight line. So let's try and draw a straight line going through them. So as you very well understand that these straight lines can be drawn in multiple different ways. Let's say this is one straight line, and let's try and draw another straight line through these points, which would be this. And we can just give it a different color, and let's try and draw another straight line through this. Let's say that straight line is going to be this, for instance. Okay, so as you can see, there are three different straight lines by which we are trying to approximate a straight line which will give us the relationship of these data points. Now, what is immediately apparent to us is that some lines are good approximations. For example, in this case, the orange line is a good approximation, while the blue and the black line are not necessarily good approximations. So what is the definition of a good approximation? A good approximation is one that optimizes or minimizes the difference between the straight line as well as the data points. In other words, the distance between our approximated line and each of these data points has to be minimized for us to get the closest possible match of giving us a linear relationship. So in other words, this orange line that we have drawn here, and this is not an exact mathematical equivalent, but remember that just by visualizing it on the graph, you'll be able to see that the orange line is much closer to each of these data points, whether that's 300, 675, 630, 1200. The orange line is closer to the overall set of data points as compared to either the blue or the black colored lines that we draw here. Now, this orange colored line, which is the closest to all the data points, is usually referred to as the line of good fit. In other words, that line that minimizes the distance between the line and all the data points. So this is an important concept for us to remember, the line of good fit. And with that, let us take our treatment further. So an important aspect of understanding regression and estimation is also to understand the concept of the variance or the errors that we see. So here, for instance, as an example, we are looking at different data points. So each of these donut data points that you see here. So we've got about 5 data points here. This is 1, 2, 3, 4, and 5. Let's say, for the sake of argument, we are able to approximate each of these 5 data points by a single linear equation, which is your good fit line. So within this good fit line, remember that there is a certain variance. So for instance, here, what we have is the average value of y. So if you were to take these 5 data points and take their average, you will get the average value of y. Now, in some cases, the value of y is above the average line. So for this one, for these 3, you can see it's above the average value of y. For these 2, you will see it's below the average value of y. So to understand the variance of this data, we have to look at 2 different things. Now, what are those 2 different aspects of variance, also known as errors? To understand that, let's first of all understand the total variance. So for this data point, for instance, this is the variance that we have from the average value of y. Let's take another example here. Similarly, for this data point, this would be the variance from the average value of y. Okay, so why is this important? Because this difference between the data point and the average value of y is the overall variance from what we usually expect to be the mean value or the average value of y or the dependent variable. So now we have to understand how to get the correlation between the y that you have as well as the good fit line that you have here, which is represented by the orange line. So remember that this total value or this total error can be understood in two different parts. Let's see what those two different parts are. So those two different parts are, first and foremost, this part here. Now this part here is nothing but the difference between the average value of y and the predicted value of y. Remember, any point on the good fit line is a predicted value of y. So this here is nothing but the difference between the average value as well as the predicted value. And this difference that you're looking at right now is known as the explained variation. This is known as the explained variation because this difference that we're looking at right now, remember, this difference can be explained by the straight line or the linear model, the line of good fit that we just looked at. So this is the explained variation. But then there is another part to this error. The other part to this error is that part which lies in between the predicted value and the real value. And this is generally known as the unexplained variation. So this is that part of the variation which is over and above or beyond the predicted value as given by the good fit line that you have here. And this has a lot of importance when it comes to understanding any estimation or regression equation or regression line. So basically, remember that this blue line out here tells us about the total variation. The total variation has two parts. The explained variation, which is nothing but the difference between the average value of y and the predicted value. And then you have the unexplained variation, which is nothing but the predicted value and the actual value right here as given by this data point. This is the unexplained variation. So the sum of these two variations is your total variation. So given this, what is the ideal scenario? The ideal scenario is that our unexplained variation is less and our explained variation is more. Now that's a good regression model because then we are able to give a correlation between changes in x versus changes in y. And that's what we eventually want to get to. We want to get to a mathematical formulation where given a value of x, you're able to then estimate or predict or forecast a value of y. So the lesser the unexplained variation, I will just mark this in a different colored font. So this is undesirable for us, the unexplained variation, and the explained variation is good for us. So the higher the explained variation, the better it is. The lower the unexplained variation, the better it is. Usually in regression studies, this is referred to as R square. And we'll deal with R square later, but for now, just understand that what we just expressed qualitatively, that explained variation is better than unexplained, and the higher the proportion of explained variation within total variation, the better it is. And that's what R square generally refers to. R square is nothing but, it is the ratio of explained variation and the total variation. So higher the value of R square, the better your model in terms of explaining the changes of the dependent variable with respect to the independent variable. All right, having looked at this, now let's turn our eye to a couple of different problems that we'll try and apply ourselves to. So here, what we have is a data set which gives us the productive hours and the revenue. So let's say there's a company, and within that company you have certain employees, certain staff members. In column B, what you have is their productive hours. Remember that the unit is in hundreds of hours. So for example, cell number B3, where the number is 23, that's 2300 hours. Cell number B4 is 13, that is 1300 hours. Along with that, in column C, what you have is the revenue. So when you see 34.72, that is 34,720 rupees or dollars, whatever you want to call, regardless of the unit of currency. Similarly, you have revenue in cell number C4. So for these 1300 productive hours, the revenue is 19,330. That's how you should interpret it. So let's say the problem that we have to solve is so given a certain number of productive hours, let's say we have to estimate the revenue. So how would we do that? So within Excel, the interesting feature is a scatter plot diagram, and let's see how we can do that. So if you were to select the entire data set, for instance, and go to the section for graphs within Excel, if you go to insert and it recommends several graphs, the one that we'll choose today is the scatter plot. So if you choose the option for a scatter plot, and then within a scatter plot, if let's say we want to remove the grid lines for now, so let's just remove the grid lines, and that gives us the scatter plot diagram. We'll just choose a different fill color just for easy visibility. So that's your scatter plot diagram within Excel. And the scatter plot diagram gives you a graphical representation of this data. This data has been chosen in a way that it makes it simpler for us to visualize it and also understand what the regression or the estimation model looks at. So within Excel, what we can immediately see is as X increases. What is X? X is the number of productive hours. We can see that simultaneously the revenue increases. So here we can say that there is correlation between productive hours, which is your independent variable, and revenue, which is your dependent variable. Now, to take the mathematical formulation further, if you just click on the scatter plot, and you will get different options like chart elements, chart styles, chart filters. If you just go to chart elements, and there is an option at the bottom called trend line. So within trend line, you will see, once you take the mouse cursor to trend line on the right hand side, you will see another small arrow. If you go there, and then it gives you different models that it can create, linear, exponential, so on. Choose the option for more options. Within more options, if you were to scroll down, and you'll see that there are options called display equation on chart and display R squared value on chart. So let's go ahead and select both of these options, right? And the trend line option out here is linear. So there we are. Once we select it, Excel gives us a way to understand the estimation. So let's look at this estimation in a better way. So let me just increase the font, and there we are. So what this estimation model tells us is that the given data can be approximated by the straight line, which is y is equal to mx plus c, where m is 1.5003, c is 0.4738. This is the y-intercept, and interestingly enough, r square is 1. So when r square is 1, which means that your entire variance in the dependent variable is explained by x. Or in other words, there is no unexplained variation. The entire variation is explained. So this is a completely linear relationship. That's why the R square is 1 in this case. So what does this mean for us? What is the implication of this? The implication of this is now you have a mathematical formulation, which we can just write here. So for instance, let's say for 2200 hours, as you can see, 22 is not a data field in this data set. Let's say for 2200 data hours, we want to estimate what will be our revenue. Now that we have an equation, we can use it. So the equation will be, we can just write it. It is going to be 1.5003 multiplied by, let's say, 2200 hours plus the intercept is 0.4738. So this out here, remove this. So this will give us the revenue. So in other words, with this mathematical equation, when your revenue is 2200 hours, when your productive hours are 2200 hours, your revenue is going to be this value right here. So with this, now we have an interesting way by which we will be able to anticipate or estimate different values. This is the advantage of using a regression or a scatter plot model for this data right here. All right, let's take a look at another example, which is again, we have production hours for a certain company in column B, and we have the salary that's being paid out in thousands of dollars. Remember, the variation in salary could be because of different reasons. One of the reasons could be overtime. So while your usual paycheck is fixed, but in some cases there might be overtime involved. That's why there's a variance, and that's why you don't probably have a straight line relationship, but we'll have to check. So let's say we want to create a model where, given this data, we want to estimate that for X number of productive hours, what would be the approximate paycheck or salary that would have to be paid out. So let's select this data and go to the option for scatter plot. Within this, let's select the scatter plot, and there we are. We have the scatter plot. Let's remove the grid lines here, and you can see that the data is quite well spread out. Now immediately what we'll do is, let's go to the options under trend line, choose the option for more options, and what we're interested in primarily is going to be the equation as well as the R square value. There we are. What we have now is this blue colored dotted line that you see here. This blue colored dotted line is the line of good fit. This blue colored dotted line is represented mathematically by this formulation here, which is y equal to 1.9804 times x. X, remember, is the independent variable or the number of productive hours right here. And then you have c, y equals mx plus c, or the intercept on the y-axis here is 9.06. So now this has given us a good equation, and the R square value is 0.8055. Now how do we interpret this value? What this is saying to us is that in the current model, about 80%, or rather 81% if you want to round off, so 80.55% of the change in Y, which is salary, is correlated to a change in productive hours. So 80% or 80.55% rather of the change in salary is explained by productive hours. This still makes it a fairly strong model. So remember that you can have different levels of correlation or R square, which is useful in different sources of material that you might be referring to. But generally speaking, any correlation which is, say, above 40-50% above 50%, I would say, can be still taken as a significant correlation between two variables. Again, remember, we are not talking of causation here. This is not a causal relationship. This is a correlation relationship, which means you are able to explain changes in one variable when there are changes in another variable. So 80.55% is still a fairly strong correlation for us. We can live with this. So let's say that we have 2200 production hours. Then what would be the salary again that would have to be paid out? Again, remember that we have an equation here. So what we can do is to calculate the estimated salary that would have to be paid out, we can simply take this and multiply this by, let's say, 2200 production hours, and the intercept is 9.0669. There we are. So this basically says that for 2200 production hours, this would be the paycheck that you will have to pay out. In fact, just make a note of one small correction here. In this data set, you can see it says salary in thousands, right? So this would not be salary in thousands. This would actually be salary in hundreds. So let's make that change right now. And I suspect the same thing would be true here. This is also going to be hundreds. Okay, so let's go back. So here we've seen another example of estimation or estimation or correlation of a linear nature. We can see, using this example, we can say that that 80.55% of change in salary is explained by productive hours. Remember the last example when we are looking at revenue and hours? Here, 100% of the change in revenue was explained by productive hours, making it an ideal perfect linear relationship. Generally, in real life, you will not see these kind of relationships. And again, 80.55 is again fairly strong. So let's move on to another example. So here we have another example. Again, we have tenure in months of associates or employees, and we have productive hours. Let's change this again. This might again be in 100 hours. Okay, so this is good. Let's select this data and see if we can visualize an initial correlation or relationship. So again, go to the charts and choose the option for scatter plot. So we have the scatter plot here. Now let's add the options for trend line. So go back to trend line. Within trend line, choose the option for more options, and trend line option here is linear, which is what we are interested in, at least as in the context of the current study, and display equation and display R square value on chart. So there we are. Let's just remove the grid lines. It'll make it easier for us to see some of the information there. And here's the font. This is better. So yeah, again, we have a linear formulation here given this data. One important thing for us to notice in this case is you will notice that the data here is much more scattered as compared to the previous example. So if we were to go back to the previous example, for instance, in the previous example, you will see that the data points are still much more closely clustered around. As you will remember, we got a fairly strong relationship here still in terms of correlation. Almost 80.55% of change in the dependent variable salary was due to the independent variable productive hours. Here, the data is more broadly spread out, but you still have a fairly medium to strong relationship. You can see that in this case, given this information, in fact, you'll notice that the R square value is only 6.3%, right? So 6.3% in fact will not even be a medium or strong relationship. It will be a very weak relationship. In other words, you could say that the change that you have in tenure does not really correlate with productive hours. In other words, we'll not be able to effectively estimate or give a forecast in terms of the productive hours in terms of tenure in the number of months. So here you can see that given this formulation, you will not be able to estimate this value just by using tenure. There might be another variable which might be at play here. That variable could very well be the productive hours and not tenure of an employee. So again, this is a good representation of how do you interpret this. Only 6.3% of productive hours is being explained by tenure. All right, so let's move on to another example here, which is going to be this. So let's take a look at this. Here we have two different data sets. We are looking at the tenure, months in a certain role of an employee or an associate, along with the training time invested in domain training. In other words, how much of time or how many hours has an employee or an associate invested in learning about their business, their industry, their sector, which is called domain training in the current year. So let's see if there's a relationship here. Going back to the scatter plots, we have a scatter plot here. Okay, well, in this scatter plot, the pattern seems to be going the other way, but let's see the values that we get from R square and the equation we get. Okay, so removing the grid lines, go back to the chart elements. We are interested in trend line, and specifically within trend line, what we want to look at are the R square and the equation values. So let's select those. We have that information here, place it here, and use the font for this for easier visibility. There we are. So we have the R square, and as you will notice here, the R square is fairly strong. So the interpretation of this R square is 98.96% of variation in training time is explained by tenure in months. So this is a strong relationship, almost close to 100. You can see by the dispersion of the different data points that they lie very close to the straight line. So this is a good strong relationship. This will allow us to predict or estimate for any value of X what the value of Y is. In other words, given the tenure in months, you will be able to estimate the training time invested in a domain year. One word of caution before we move on. Remember that when you do conduct an estimation exercise, please make sure that the data point for which you're trying to estimate is within this range. So what do we mean by that? So if you look at this, our range in terms of tenure of months goes all the way from 6 months till the maximum, which is 49 months. So this model will work for us as long as our X or our tenure in months in role lies between 6 months and 49 months. Let's say you were asked to estimate the training time invested in domain training in current year for, let's say, somebody whose tenure in terms of months was, let's say, 100 months. Now, since 100 months is far ahead of this scale, it will be difficult for you to apply this model. You can't just extrapolate the data set like that, right? So even when you're conducting this exercise from a regression standpoint, it is preferable to only estimate the value of the independent variable basis the value of the dependent variable basis the independent variable for this range, because this is the data range from 6 months to 49 months is the data range for which we have conducted this regression study. So I would highly recommend that we don't blindly extrapolate the model to those data points that lie beyond this range. Finally, is this only going to be useful for us for those data points that seem to cluster around straight lines, in effect following a linear relationship? Not really. We'll take another example. Let's say, so here what we have is a different data set. In column C, we have time in seconds. In column D, we have speed. So this is data for a projectile. Let's say there's a projectile for which we have collected data. Column C has time in seconds, so this is time of flight, the number of seconds that the projectile has been in flight. Column D has speed, so the speed in terms of meters per second for that projectile. Given this, let's see what we can gather from a scatter plot. So we go back to the graphs, we go to scatter plot, and there, immediately, the moment you draw the scatter plot, you will notice that this does not seem to represent a traditional linear relationship. In fact, this is very close to what you'd expect to see from a parabolic relationship. Let's move the grid lines. And this time, when we go to trend lines, what we'll do is, instead of selecting the linear option, we are going to go ahead with selections of polynomial. So remember that a parabolic relationship or a relationship of order 2 can also be taken as polynomial. So we'll choose polynomial right here instead of the usual linear relationship, and we can display the equation. There we are. We have the equation right there. So as you can see here, let's just remove this one if we can. There we are. So this is an example of a non-linear relationship or correlation between different variables. Here you can see that the maximum power of the independent variable x is the power of 2, not the power of 1. So this is a typical parabolic relationship. So regression is not limited, strictly speaking, to linear regression or linear correlation only, but that's a much more advanced topic outside the purview of today's video. We will deal with this in a future video per se. So just to quickly summarize some important aspects of what we've looked at today. So remember that when you have a data set, always start off with a graphical representation if you can, to get a grasp or get an intuitive feel of what that data set really means. You can use different graphical tools, whether they are scatter plots. In some cases, you could also use things like dot plots, stratified plots, and so on. When both of your independent variables are both continuous or both discrete, a scatter plot is a good tool to give you a preliminary intuitive feel of what your data might look like. Once you've done that, you could possibly apply any of the linear regression models to see if there's a line of good fit. That means if there's a line which can approximate the data points that you have. Given that line, you could then take a look at what is the equation, what's the value of r square. Remember, as a rule of thumb for now, what you can do is any r square value that you see greater than 50% or 0.50 could be a moderate to strong relationship. Obviously, above 75, it's a strong relationship. Any values of r square that you see less than 50 might be weak to moderate relationship. Another important thing to bear in mind is do not think that a correlation is necessarily an artifact or evidence of causation. Just because two variables change with each other don't mean that one variable causes the other. Another thing that I would advise you to bear in mind is do not just blindly extrapolate data outside the range. So if you have established a linear relationship between a set of independent and dependent variable, when you do apply it to estimate values, please make sure that the value of the independent variable or the value of x that you take for that lies within the range for which you've conducted that study and not outside it. All right, so that was hopefully a simple introduction to some of the regression tools that you can use within Excel. It's a primer or a beginner to looking at what it means to forecast or estimate data using basic information for dependent and independent variables. And we'll obviously try and extend it in future videos. So thank you so much for watching. See you next time.